this kind of density function fzz equals to 1 upon under root 2 pi e raised to power minus z square upon 2 for all z belongs to the set of real number. And this is the graph of the standard normal random variables density function. And then we have calculated its variance 1 and expectation 0. And then we have also find this probability distribution function or cumulative distribution function, capital F x. But for this standard normal distribution, we represent its capital Fz instead of this special capital phi. Capital phi x representing the cumulative distribution function for the standard normal random variable denoted by this phi function, and it is defined by that the probability of z less than equals to x. In general, it is actually like if this is the graph of the fz, you can see. Then if this is the line x equal to 1, this is the line x equal to 1, then the area from minus infinity to this x underlying this curve actually value of the phi x. So for each and every x on the real line, we have calculated and created a standard distribution table. And this is the some property of the this standard normal distribution function, that its cumulative function phi of infinity is 1, phi of minus infinity is 0, phi of 0 is 1 by 2, phi of minus x is equals to 1 minus phi of x. Then we have solved one example also, and these are the some result we have also proved in the last class. This is like if z is a standard normal random variable and we define some x like this, sigma z plus mu equal to z x, then this x becomes normal random variable with mean mu and variance sigma square. And then another thing we learned here, that if we have some normal random variable x with mean mu and variance sigma square, then we can calculate its cumulative distribution function with the help of in terms of standard normal distribution function, like capital phi x minus mu upon sigma square, x minus mu upon sigma. And in this way we can calculate the probabilities also. So like probability of x greater than a less than equal to b, and here we know that x is equals to a normal random variable with mean mu and variance is sigma square. Then this probability, earlier it actually this one equal to this one. Earlier it is actually f x b minus f x a. Since but then there we have, here we have capital X, but now we are having 5. So when we are writing 5, we write like b minus mean upon standard deviation sigma square root of variance minus phi a minus mean upon sigma. So this probability for a normal distribution can be written in terms of the standard normal distribution, like a distribution function of standard normal distribution. So if x is a random variable with mean mu, x is a normal random variable with mean mu and variance sigma square, then x minus mu upon sigma becomes a standard normal random variable with density function phi. And then we have solved one example like this. Try to, like if x is a normal with mean mu and minus 5 and variance sigma square equal to 4, and from there we have calculated mu equal to minus 5 and sigma equals to 2, And then if I want to know what is the probability of x less than 0, actually it is probability that x less than equal to 0. And in terms of a distribution function for the random variable x, it is fx0. Now here x is a standard normal, not x is a normal random variable with the mean mu equals to -5 and sigma equals to 2. So its distribution function can be rewritten as in terms of standard normal distribution function phi with the values like this x minus mean is -5 upon sigma. And after simplification, we are getting x equals to 2.5. Now from where we can get this value phi of 2.5. To get this value, we open this table. This is known as a standard normal cumulative distribution table. So here you can get all the values like there this is z, or we can say it's x also. And then we will see that actually 2.5 is there. If you see now, so 2.500, so it means 2.5. So capital phi of 2.5 is 0.9938. So from that table we will see, and then we will get this one. Okay, similarly we can see the value of phi 1 also. So phi 1, again we go to this phi 1, 1 is this one. So 0.84143. And then so like this we can write values from this distribution standard normal distribution table, and this table is provided to you at the time of exam, so that you can see the value of phi from this. Like if I give you like phi of 1 point like 1.1, so you will get here like this is 1.1. And if 1.11, then it is like this, because 1.1 is already here and 0.01 will get this, so this is the value like 1.15. So you will go to till 5, and you know this is the column for 5. So this is the value of 1.15. So this is the table for standard normal random variable z, and from there you can uh, see the value and substitute there. So this is already discussed. Another result is that if x is a random variable with mean mu x and variance sigma x square, and we have another random variable y is actually ax plus b, where a and b are two real numbers. Then y is also a normal random variable with mean mu y and variance sigma square, where the value of mu y is given by a mu x plus b, and variance sigma y square is given by a square sigma square. So if you have any random variable, so earlier we are having like z is a random variable, and if from z we can write x like in this way, sigma x z plus mu x, then x becomes a normal random variable with mean mu x and variance sigma square. And now in this theorem what we are doing, we have a x is a normal random variable with mean mu x and variance sigma square. And now we are creating another random variable that is actually ax plus b. And then for this kind of random variable, we can get their mean and variance from this mu x b, a mu x plus b, and variance a square sigma x square. So we know that x can be written as in terms of standard normal variable like this, and then we substitute this value of x in this expression. If we substitute, we will get this one, and then this, after simplification, you will get this one. So here this becomes actually your sigma for the new random variable y, and this becomes the mean. So the mean is this a mu x plus b, that is mu y, and where this is sigma, so its square is variance, so a square sigma s square is the variance. Because if you have z as a random variable, as a standard normal variable. So this coefficient is the variance or standard deviation of x, and this is the mean. So from there we can see that now this y can be written as in this form, and the coefficient of z is this one. So it means this is the standard deviation of y, or its square is the variance of y, and its square is a square sigma x square, and this part is the mean of the y. Then we have gamma function. So gamma function, like in your second semester or third semester, I think you have learned this thing. So this is gamma, like if alpha is greater than 0, so we define gamma function like this: gamma alpha equals to 0 to infinity x raised to power alpha minus 1 e raised to power minus x dx. And if n is any integer, then gamma n can be written as so like n belongs to this 1, 2, 3 something, then gamma n can be written as n minus 1 factorial. And there you have also learned that gamma 1 is having value 1, and if alpha is greater than 0, any real number, then gamma alpha plus 1 can be written as alpha into gamma alpha. And if it is a positive integer, then in fact it can be written as gamma n plus 1 equals to n factorial. So these are the some results. You remember this is the definition of gamma function. Gamma alpha is equals to 0 to infinity x raised to power alpha minus 1 e raised to power minus x dx. Then gamma alpha plus 1 equals to alpha gamma alpha for alpha greater than 0. Gamma n equals to n minus 1 factorial for n goes to 1, 2, 3. And gamma 1 by 2 equals to root pi. So these are the results related to gamma function that we will use later in some calculation. For example, we will see how we use these results. And these kind of, you already know all these things from your second, third semester studies. So you can go there. And so like if I want to know what is the value of gamma 7 by 2, so gamma 7 by 2 can be rewritten as with the help of property 2. It can be rewritten as like gamma 7 by 2. Gamma 7 by 2. So it can be rewritten as 5 by 2 plus 1. So it is like alpha plus 1 something. So you can write it gamma 5 by 2 and 5 by 2 like this. So that's why we're using property 3. So similarly, this 5 by 3 again can be written as 3 by 2 plus 1. So again using property 3 in this part. Then 3 by 2 can be written as 1 by 2 plus 1, then this. And gamma 1 by 2 is root pi. So this is the value of gamma 7 by 2, 15 by 8 root pi. Now like this kind of integral if you have, then it is difficult to do this integration by part because it's having x raised to power 6. So it takes time. So you use the gamma integration property because it is 0 to infinity x raised to power 6 minus e raised to power minus 5x. So using this expression, this 0 to infinity x raised to power minus alpha e raised to power minus lambda x dx equals to gamma alpha upon lambda alpha for lambda greater than 0. It will like this. So it is in that form. Instead of 6, we can write it 7 minus 1 because 6 can be written as 7 minus 1. So gamma 7 upon 5 raised to power 7. So these property you can use to calculate integrals. Okay, then there are some problems. You try all of them. So like here we have next kind of random variable like this is continuous in this. So the can mix then then join distribution with okay. So two case of two random variables. More if you are having more than two random variables like in real life, we are often interested in several random variables that are related to each other. For example, suppose that we choose a random family and we would like to study the number of people in the family, the household income. So another variable, number of people in the family, one variable, random variable, household income, another variable, age of the family members, another random variable. So like if we have more than one from same distribution, we want to study more than one property, so we have more than one random variable. So if suppose we are having two random variables x and y, so earlier you have only this term probability mass function. Now if you have having more than one random variable, then this term additional comes to this joint probability mass function. Okay, we will come to this later. Wait a minute. So I think this PDF is also visible to everyone, and we have already discussed this result also. Expectation of x square minus expectation of x whole square is variance of x, and variance of x is denoted by sigma square, and sigma is known as the standard deviation. It is the square root of variance of x, and then this is also we have discussed. Okay, suppose we have this problem. Let x be a random variable with probability mass function. Probability at x equal to xi is given by this expression k e raised to power minus t 1 minus e raised to power minus t raised to power xi minus 1 for I goes to 1, 2, 3 up to infinity. So find the value of k and mean of this probability mass function. So first you have to identify what is the range of x. So here like xi is the values are taken by the random variable capital X. For I goes to 1, 2 to infinity. So you can write this is the range of x, x1, x2, x3. But we found that here it is given that xi is actually I. So it means x1 equals to 1 and x2 equals to 2 and x3 equals to 3. So finally the range of this random variable is 1, 2, 3 up to infinity. Now the expression for probability mass function is k e raised to power minus t 1 minus e raised to power minus t whole raised to power xi minus 1, and we have to calculate this k. So, and we know that since it's a probability mass function for the random variable x, so its total probability will be 1. So we'll use the sum of the probability mass function over the all values of the range set of x. So we are adding this one, and then you write the value because xi is I. So here probability that x equal to xi, this one k, this, so we substitute this value here. So after substitution we are getting this k e raised to power minus t 1 minus e raised to power minus t raised to power xi minus 1. But xi is actually I here in this particular case, so it will be like this. And then this k and this e raised to power minus t is independent of the index of this summation, so they will be out. And finally, you are having this one. And then the summation can be expanded like this: 1 minus this is square, and whole cube like this up to infinity and equal to 1. And you know that it's a geometric series with common ratio 1 minus e raised to power minus t. So its sum is 1 upon 1 minus this. And then you simplify it, you will get 1 upon e raised to k e raised to power minus t, and this you will get 1 is cancelled out by minus 1, and this e raised to power minus t will remain here, and that will be cancelled out later by this one. So finally, you are getting k equals to 1. So you once you have obtained the value of k, you have substituted in this probability mass function. This is the probability mass function for the random variable x. Now you have to calculate its expectation or mean. Mean is from the definition is xi and probability at xi. So, but here xi is actually I. So you can write summation I goes to 0 to I goes to 1 to infinity I, probability that x equal to I. Probability that x equal to I is actually this one. So you have written this one here. And then this e raised to power minus t is independent of this index of the summation I. So it will be out, and you are having this one. And finally, you expanded it, and you will get this one. You know that this 1 minus x raised to power minus 1 is having this expansion, 1 plus x square like that. So if you like try to calculate this expansion, 1 minus x raised to power minus 2, that it maybe you have calculated in your 12th standard. Actually, this one is this one, 1 plus 2x plus 3x square plus 4x cube like this. And here x is actually 1 minus e raised to power minus 3. So this expression can be rewritten as 1 minus x raised to power minus 2, where small x is actually 1 minus e raised to power minus t. So we have used this result here, and after simplification we are getting mean as t. Now here again, let x be a random variable with the probability density function fxx equals to k e raised to power minus of mod x, and x lies between minus infinity to infinity. So find the k that you have already calculated in the exam, test exam. Mean, variance, and fifth moment about origin need to be calculated. So to calculate this mean of the first, we try to calculate the value of k. Since it's a probability density function, so its integration from minus infinity to plus infinity is 1, because this is the property of density function. And then you have substituted its value, because for all values of x from minus infinity to plus infinity, it is having single definition, this one. So we have substituted here. Now you can see this mod x is an it's a mod value. So within this domain, this is actually even function of x, and you can use the property of definite interval integral. If you use the property of definite integral, it can be written as 2 times of 0 to infinity k e raised to power minus of mod x, because this part is an even function of x. So it can be rewritten as in this one. Now since the domain of integration is 0 to plus infinity, and in the definition 0 to plus infinity, mod x is having definition x. So we will write because when x is greater than 0, mod x actually x, and when x is less than 0, mod x is actually minus of x. So since here in this domain of integration x is greater than 0, so mod x can be replaced by simply x, and then its integration is e raised to power minus x upon minus 1. Then you substitute lower limit and upper limit. For upper limit it is 0, for lower limit it is like this. And after simplification you will get the value of k as 1 by 2. Now we have to calculate its mean. To calculate its mean, We know that mean is expectation of x. It is x into density function of x. Density function of x is x dx. And then you write its definition. Its definition, we have substituted the value k here. K is 1 by 2. That's why there is 2 in the denominator. Earlier it is only k into this now, and k we have obtained here as 1 by 2. So we have substituted its value. So now this becomes the density function of x. So x into this dx. Okay, now you can see that this is a even function and this is an odd function. So this is even, this is odd. It means in totality, this product is a odd function. And if this product is a odd function, the integration from minus infinity to plus infinity is zero from the property of definite integral. So it means mu is zero in this particular example. Now we try to calculate variance. So to calculate variance, we have this formula. Variance of x is actually expectation of x minus mu whole square. So instead of calculating this, because we have already obtained the expectation of x, that is it turns out to be 0. If somehow we calculate expectation of x square, then we can calculate the mean variance. Or directly here in this case, since mean is 0, so we have substituted the value of mu is 0. So it means expectation of x square in this particular example becomes the variance of x, as expectation of x is 0. Now you can write like x square because it is expectation of x square. Actually, it is not well written here. We take care of this thing in exam. It should be written like this. X square, not like this. We write like this. Okay. So if this is expectation of x square, so you know how we write the definition. The definition is x square and it's what we call this density function. So x square into density function, and within the domain minus infinity to plus infinity. So we have substituted the value. The value is we have calculated 1 by 2 e raised to power minus x, and this is x square. So this is even and this part is also even. If both function are even, then their product is also an even function, and then provide the property of definite integral. It is 2 times of 0 to infinity x square e raised to power minus of mod x upon 2 dx. And in this domain, 0 to infinity, mod x actually defined as x. As in the when x is greater than 0, and in this domain 0 to infinity x is greater than 0, so mod x simply replaced by x. Now you have this one. So you to calculate this one, you use your what you call integration by parts, or either you can use here gamma function also. So he used this integration by part. So integration by part like a first function as it is integration one time integration of second, then different one time difference minus sign one time differentiation of first and two time integration of second, then plus one more time differentiation of first and three time differentiation of second, and then because it's x square, so goes to 0 to infinity, from minus infinity to all 0, and for x equal to 0 this term becomes 0. Only we will get something from here, that is 2 into e raised to power 0 upon minus 1, and finally 2. So the variance of this particular question is 2. Now the moment about mean. So moment about mean is expectation of x minus mu raised to power 5. But here mu is 0, so it is expectation of x5, and expectation of x5 it is like x raised to power 5 and density function, and then this one is even and x raised to 5 is odd, and then from the property of definite integral it is 0. Then we go to the multiple random variables or vector of random variables. So consider a random experiment in which a die has rolled and coin is tossed. Let x be a random variable whose values is equal to the face value of the die, and y be another random variable which takes 10 value if tail turns up and take 20 value if head turns up. So, so x is the face value of the die and y is the random variable which takes 10 if the head turns up, and if tail turns up then it will take 20 value. So like we have one, in this case we have one sample space is this one and another is this one, because it's a throwing of a die and it's a throwing of a this to the coin. And now x is taking 1 to 1 because x is a random variable. Whatever face value is the coming, that face value is the value of the random variables. So like this event 1 is going to 1, 2 is going to 2, 3 is going to 3, and this face value 4 is going to 4 real number. So this is the very defined x. Now comes to y. Y, if tail turns up is take 10 value, if head turns up it takes 20 value. Now we created another sample space S, which is the Cartesian product of these two sample spaces. And you know that if S is this one, S1 is this one, S2 is this one, then Cartesian product is written as this 1h, 2h, 3h, 4h, 5h, 6h, and then 1t, 2t, 3t, 4t, 5t, 6t. So this is the Cartesian product. Now this is like a combined event. So now our x takes values in what way? So like if the event is 1x, because now we are having two random variables, and now event is this one because this is the element of capital S. This is actually small s. So this is actually small s. This one is a sample point. So this random variable x takes to this sample point. We use this earlier definition because x is for face value. So whether it here is h or here is y, its x is taking it to 1. Similarly, x2 is going to 2, 2 tail is also going to 2, 3h is also going to 3, and 3 tail is also going to 3. So like this we do. Now we go to y. Y we know that this y is mapping this tail to 10. Tail here. Reference value y take another okay. Is take if tail turns up, it will take 10 value and take 20 value if head turns up. Okay. So for head it is taking 20, for tail it is taking 10. So here 1t, 2t. So it's actually y is when variable for this tail. So it will take all these sample points to 10 and all these sample points to 20. So now we write like earlier we are mapping sample space to one real line, but here we are having two random variable. Now this S, the sample space S, and its event small s, like this is your like this is our sample space capital S, and here this one is some event Si. So this is actually now is mapped to some point on the two-dimensional space. One is for x, another one is for y. So this is line for the random variable x, and this is line for the random variable y. Random variable capital X. So and then this event is mapped to like if Si is the event. So having face value 2, and like if say Si is having this kind of event to tail. So if two tail is the sample point in the sample space, then two tail is actually mapped to 410. 210 actually. This is 210. This is 210. Because on x-axis it is taking 2 value and on y-axis it is taking 10. So this sample point is mapped to 210. Similarly, another like if you have another value like 2 head instead of tail, if you are having 2 head, then like 2 head is if this is the event in the sample space, then it is not mapped here. Now this is mapped to this 220. So now because we are having two random variables, so these are taking sample points to different in the plane actually. So earlier we are having like when we having an event x less than equal to x, we are saying that this is the event earlier. So it means we are talking about minus infinity to some x on here. Similarly, if we have another event, then minus infinity to some y. So now if we are having x point in y point in here, so we will have like one line here, and then all the domain below it is considered as. We'll see this next page. So this is the way we are mapping sample points in the two-dimensional plane through the two random variable capital X and capital Y. So the sample point S, now earlier we are having this only one random variable X, now we are having two random variable X comma Y, and they are taking the sample point S to the point X comma Y, where small x is corresponding to this capital X and small y is corresponding to capital Y. It means x of S is a small x and y of this S is actually small y. So now we are mapping this sample space of, into with the help of two random variables. So suppose x and y are two random variables defined on some sample space where specific values of x and y are x and y respectively, then any ordered pair xy may be conveniently considered to be a random point in the xy plane for the vector random variable x and y. So it's, sometimes we say it's a two random variable because we are having two. Sometimes we have more than two also like x comma y comma z or something like x1 comma x2 comma x3 comma like. So sometimes we call it a vector of the random variable. So you know that like in the case of one random variable, we define event like this. If A is the event, x less than equal to x. Okay. Similarly, event P can be defined to Y. We have defined another event B, and B is actually this one. So the events A and B refer to the sample space S, while the event this intersection is referred to the joint sample space as A, and we will write like this. And I already told you that if we have comma in these kind of events, it means it is actually intersection. So we will see through this figure actually. So like here we have this event A, x less than equal to, like suppose this is our sample space S, and two events A and B are there. So event A x less than equal to x less than equal to x, like if I'm drawing is this vertical line which is x equal to, which is line this capital X equal to x line is this one. So x less than equal to x means all the points left side of this line because all these are lying in this domain x less than equal to x. Okay. So if I'm talking about this less than equal to x, then this event actually is all the points having a image in the sample space. Similarly, y, if this is the line, suppose y equal to y line is this one, then all the points below it actually representing this event b. So this is for b, y less than equal to y, and this is for x less than equal to x. So you can see, if I am talking about the intersection event, this domain. So this domain is actually mapped to this because this is the event intersection, whatever actually is mapped to this one. So this is the way we define like a two-dimensional random variable x less than equal to x, y less than equal to y is actually intersection of these events. So this is the event. Hmm. So this event is of interest to us, and it is noted by this x less than equal to x, comma y less than equal to y. So this is the notation to define the event for more than one random variable. And what is the meaning of this event is actually this x less than equal to x intersection with y less than equal to y. And you know the meaning of this. Meaning of this is if you have a sample point S, you have to consider those sample points here whose x image is less than x and whose y image is also less than y. Then they belongs to this event. So event A correspond to all point in the Sj. So while x coordinates values are not greater than x, similarly event B is corresponding to the y coordinate Sg not exceeding y, and the joint event is A intersection B corresponding to this. Actually, this is interest to us for the case of two random variables x less than equal to x and y less than equal to y. It is actually A intersection B, and A is actually x less than equal to x only, and B is y is less than equal to y. So now joint distribution function. So whatever this event we are having for the case of two random variable, so the probability of this event is called the joint distribution function. So this new word actually come here, joint. Earlier only distribution function we were having. That one is actually this f x x, and that one is actually probability of capital X less than equal to small x. Okay, but when we are talking more than one random variable like joint distribution, then the probability, because now in joint we are interested of this kind of event. So the probability of this event, probability that x less than equal to x, comma y less than equal to y, is called the joint distribution function for the random variable x and y, and the notation is like capital F x comma y x comma y. Here this small x is for this capital X, this small y for this. And other properties are also seen because we have seen for the case of single random variable. Like if x and y both are infinity, then this probability is zero because there nothing is there for intersection. If one of them is infinity, like x is minus infinity, so if x is minus infinity, it means this event is empty, and intersection of empty event with this is empty, and finally you will get zero probability. So if y is equal to minus infinity, it means this event is empty, and intersection of empty event with any event is again empty, and the probability is zero. Then like marginal distribution function. So what we have here in this case of marginal, like if I replace here, like here we are having two variable f x y, and if I replace y by plus infinity. So if I replace y by plus infinity, like if I'm talking about this event only, and in this event y less than equal to y, and small y is plus infinity, it means it's now it's actually become a whole sample space capital X, because y is actually plus infinity, small y is plus infinity. So whole sample space is intersecting with this event. So if we are like, because all events are subsets of this sample space, so S intersection will this will give you only this event. Similarly, if x is infinity plus infinity, then you will have only this one. So that one is known as marginal distribution. So marginal distribution functions are f x y x comma plus infinity. That is probability that x less than equal to x and y less than equal to plus infinity. So y less than equal to plus infinity will give you the whole sample space for y, and whole sample space intersection with one event, actually event will be remaining. And if this is the case, so it is actually distribution function for the random variable x. Similarly, infinity y will give you the whole sample space of for x, and s intersection with this event will give you this event, and finally it's this distribution function for the random variable y. And if both are infinity, then say this is s, this is also s, and the intersection is again sample space s intersection s, and the total probability is 1. Now if you have more than two variable, like if you are having x y z are three random variable, then their joint distribution function is f x y z, x comma y comma z, probability that x less than equal to small x, y less than equal to small y, and z less than equal to small z. And if you are having n random variable, in this way you go. Now if once you have this distribution function, then you can also calculate their density function. So earlier that one is known as probability density function, now it is known as joint probability density. So how you calculate? Earlier it's a differential derivative of the distribution function, because here we are having two random variables. So the joint density function is given by this expression: del 2 del x del y fx y x. And similarly, like from density joint density function f x comma y, because this is joint density function f x comma y, you can calculate its joint distribution function also, and the joint distribution function can be calculated with the help of or from joint density function through this: u goes to minus infinity to x, v goes to minus infinity to y, fxy uv du dy. And other results are also like this. Earlier you know that like we are having that much in the like probability that x1 less than x less than equal to x2. So what you write? F x x2 minus f x x1. So if this additional event is there, so we will use the same result, keeping this y as in comma. So fxy x2y comma fxy x1 y. Similarly, if y is having value from y1 and less than equal to y2, so we will write the result for y2 and keep this x as it is: fx y2 minus fx y1. And if both are there, then we have this fxx2 y2 fxy x1 y1 minus fxy x1 y2. And you have to remember these results, because we will use all these to calculate the probability. Property of joint density function. So like the case of single random variable, It is also greater than equal to 0 for all values of x and y. Within the domain minus infinity to plus infinity, this value is greater than 0. Earlier, the integration of a density function within the whole domain is 1. But here, since our domain is for x is also from minus infinity to plus infinity, and y is also from minus infinity to infinity. So this double integration of joint density function should be equal to 1. So this is the property of joint density function for the case of two random variables. Now, joint probability mass function. So like you have two discrete random variable. One is x having values this x1, x2, xn in its range set of x, and y is another discrete random variable taking range of values y1, y2, yn. Then Pij representing the probability joint probability mass function, and it is denoted by this probability that x equal to xi comma y equal to yi. Earlier, only this part can give you the probability mass function for x. Now, comma y equal to yi means this event intersection with this event, and the probability is known as the joint probability mass function for the random variable capital X and capital Y. Earlier, because it's a single random variable, so for one random variable, this sum should be 1. But now we are having two random variables, so this double summation Pij equal to 1. If we had three, then triple summation Pijk like this. Then how we calculate this joint distribution function for the case of two discrete random variables? It is earlier it is defined by this for the single variable that x less than equal to x. But since we are having here two random variables, so the joint distribution function xy probability x less than equal to x, comma y less than equal to y, comma means intersection of these two events. And then we have earlier we have single summation, now we have double summation xi less than x and yij less than y and probabilities of these points. If we add them, we will get the joint distribution function for the case of discrete random variable. So we go through all these concepts because this kind of question I asked earlier in almost every exam. So you read all these, and other thing you can do, you also read from here also. The same thing they are also talking about. So like for joint probability mass function is denoted by this, and this is probability that because it is taking right now it is talking about mass function. It means random variable is of discrete kind, and for discrete kind this is the joint probability mass function. And I told you this comma is means for it's the intersection of these two events. So this is the intersection, and whatever probability we will get. This is like joint probability instead of double summation. He has written this in a paired sense. So, but it is difficult for you to imagine in paired sense how this summation is going on. That's why in notebook it is in the sense of double summation, so that you can easily understand that. We are there. This one double summation is there. Then marginal and all. We will also talk about all these things. So I stop here and we go through this concept of vector of random variable from this notebook. And, okay. Okay, then we'll talk about tomorrow about this.